So none of this should be different. So the derivative of the sine, cosine. Derivative of the cosine, the opposite of the sine. Tangent, maybe you have to peek at that one, secant squared, right? But derivative of e, thank you. And write yourself a note, the fact that e is a constant. The only time that you need to worry about e is when it's e to the x. But that's no different from a to the x, because when you take the derivative of a to the x, you get a to the x times the natural log of a, which is why this one is just e to the x, because the natural log of e is 1. That's why that goes away. So these two are the same thing. So if you have your choice of which one to memorize, do this one. Because if you write e to the x natural log of e, the exponent on e that gives you e is, that's why that goes away for here. Same conversation down here. Every time you take the derivative of x, make sure you know that that's 1. And when you're doing this, if it's involving things that are added or subtracted, that 1 is a placeholder. He counts. If it's 1 as a factor, then, it goes away. Anything times 1. So pay careful attention to whether you are adding or subtracting the derivative of x, because then that holding on to that 1 matters. The same relationship here. The natural log of x is going to be 1 over x. When we have that log conversation, it's going to be 1 over x times the natural log of a. But keep in mind, that's why this goes away. Because the natural log of e is again 1. So that should be in your brain by now. You've had enough practice of it. If you do things enough times. Now, as soon as you stop doing calculus, I don't know, let's say we stop. Your graduation date, I think, is June 2nd. So, right? June 1st? So we'll stop doing calculus on June 1st. Like by July, you'll be like, I totally forget everything. But it's back there hidden. So if you take calculus again in college, it'll be easy for you to pull back up, which is the purpose of why you're here. So I think a lot of kids are struggling because they're like, wait, this is hard. I thought I signed up for the easy calculus. There is no easy calculus. We just have a gift of not having that AP test, and we have the gift of slowing down if we need to. All right. So here's my answers. I want to make sure, this is on the test. I'm putting it in front of you on purpose. So I want to make sure that you understand how to do these problems. So don't copy. Copy and see if you understand it. So do me a favor and talk to your friends and try to make it work, and then come back. So I'm trying to figure out, you need to be able to tell the difference between the first two and the second two. The first two are algebra 2. The first two, and Caitlin, you can move up to a seat if you want to move closer. There's this seat here by Adrian. There's a seat here by Brady. You can move if you want. Okay, these first two, that's algebra 2. That's that composite function. That's a function within a function. So what this means is, take care of this first. Tell me when 1 goes into H, what comes out? 3. So then when 3 goes into G, what comes out? Algebra 2. What you need to know is these two things say the same thing. So if you want to rewrite this as H of G of 3, you can. 3 goes into G, what comes out? 3 goes into H, what comes out? Are we okay there? Algebra 2. Everyone's okay with that? Okay. So this is not enough room here. So I'm going to draw this squiggly line and I'm going to call this number 1. So I'm going to do number 1 with you, and then you're going to do number 2 with your partner, okay? So the change in this one represents, now I'm finding the derivative. So I want to find the derivative when the input value is 3 of this function. So if I have the derivative of this function, I have to apply the chain rule because I have an inside-outside. My outside of my function is h of x, or h of something. My inside function happens to also be h of x. So I have to apply the chain rule. So what this ends up being is the derivative of that, and then what's inside of it remains the same. And then I'm going to multiply it by the derivative of what's inside. So here's my outside function, and here is the derivative of the inside function. So when I go to do my values, b prime of 3, I'm substituting 3 in for these values. So what I need is, the same as we did this piece by piece, 3 goes into h. What comes out? 2 comes out. So this is equal to 2. Now I need to find h prime of 2 times h prime of 3. H prime of 2 is square root of 2. H prime of 3 is -1. So therefore my answer is the opposite of the square root of 2. So when you go to set up the second one, make sure you're thinking chain rule, make sure you're thinking derivative. Here's my function. Your outside is g, your inside is h. So f prime of x is going to be equal to the derivative of your outside, and that inside function is just repeated, times the derivative of the inside. Take a minute and see if you can set it up while I'm not talking. Go. So check your work with mine. And the biggest thing about the chain rule that you need to make sure that you're understanding is that derivative of that first part includes what's inside, and that's just repeated. And then we take the derivative of the inside. So you wanted to make sure. It's funny, I think the charts are meant to be easier, but sometimes they can end up being more confusing. For sure. Questions on that? This is a G, that's a G. Sometimes my G's end up looking like 8s. Sorry. Except I make my 8s like snowmen. I'm thinking snow. All right. I have a couple more things that I want to make sure that I put in front of you. And it goes like this. Can I take this away, or are we still looking at it? Take it away? Okay. Our notes last class had us talking about higher order derivatives. Our notes last class had us talking about higher order derivatives. So when I take the first derivative of a function, I'm looking at the instantaneous rate of change. So this is somebody said to me, why are we doing this? So I want to make sure you know, this is our instantaneous rate of change. Our second derivative, that's when we talk about acceleration. And I thought I talked about that when I showed you the two graphs. It talks about how fast the tangent is changing. So if I have something changing, that's my instantaneous rate of change. But then when I'm talking about how quickly my derivative is changing, I'm looking at my acceleration. And then my third derivative is called jerk. Not kidding. So your third derivative is referred to as jerk. So we're going to be applying these in word problems and application next unit. So right now we're just practicing on how to do them. Make sure that you pay attention to the notation where I'm talking about the second derivative recognizing d squared, and then it's as compared to the change in x squared to that second level. So make sure you pay attention to where those exponents are in the notation. As you know from last time, notation matters. All right, so we worked through these together, no problem. Finding my second and third derivative and if it's a situation where you implicitly, and here's the difference between explicit and implicit. If it's an explicit function, y is already explicitly solved for. So there's really nothing for you to remember because you're not taking the derivative of y because it's already happening down this outside. So if it's an explicit function, higher order derivatives, you're just finding the derivative of the derivative of the derivative, no big deal. If you have an implicit situation, because y is somewhere in the middle of the equation, you're going to be taking the derivative of y, and you're going to end up with the dy dx. So when you solve for dy dx, you have a chance of still having a y in the equation. So when you go to take the second derivative, and you end up with a dy dx, what you need to do is substitute what dy dx was equal to in, and then continue going. Now the one we gave you here was pretty complicated and you were like, whoa, that's terrible. But if you continued working, this one was not hard because y was already isolated. So I found the derivative and then I found it again. And again, that notation is super important because we need to know when we're simplifying and when we've moved on to the next derivative level. Here we need to know when we've moved on to a derivative and when we're simplifying. So keeping track of that is super important. These were not a big problem because they were explicit. Y was already solved for. When we get down to here, we had two implicit examples. And what was interesting was they already gave us what the first derivative was. So when we found the second derivative, our job was to plug in that into for the dy dx. So if you consider the homework that I gave you, if you did the first couple of problems, I think the first two problems took me longer than the rest of the entire worksheet. If you got discouraged right around here, I was feeling your pain because I was also as discouraged. So I'm like, shoot, this takes forever. But I found myself getting better at it and having less of a drama. And then having the answers at the bottom, I found so very helpful, and it was rewarding when I'm like, okay, I did it right. So does anybody have any questions here on any of these ones that they couldn't solve? The first one? So when we talk about the first one, when I go to take the derivative of this one, it's the product rule. So it's the first term times the derivative of the second, which is just e to the x, but having those boxes make it easier for me to see it. Okay? And then times, so the first term times the derivative of the second, and then I had Um, yeah, because this -1 is the derivative of that. First term times the derivative of the second plus the derivative of the first term is 2 times the second. So this term here, this is my first term. This is my derivative of the second, plus, here's the derivative of my first term times my second. So then when I simplified things, it's just this negative came out here with the 2. So -2x e to the -x plus 2 e to the -x. So it was time to take the second derivative. I had the product rule again. So then here's my first term times the derivative of the second plus, and then this is just the derivative of that. It's all about, and like, whether or not you separate out this 2 e to the x and leave yourself with x minus 2, nobody cares. If you left it like this and had all the parts in, it would be fine. I find the product rule the hardest one because there's so many different orders that you could do it in and still be right. Anything else on the homework? Because I want to make sure that I get to the review packet. Go ahead. Second one on the back page. I had to add my Post-it note to that one, Ricardo. So for that second one, 3 times y to the 1 less power dy dx plus 2 dy dx equals 3. So solving for dy dx in this one wasn't so bad. I factored out dy dx, divided by that, so I was feeling pretty good. Then it came time to take the derivative of this, and I had to do the quotient rule. Low d high, because that's a constant, minus high d low, and don't forget your dy dx. Square the bottom, and away we go. So then it was all about simplifying, because this goes to 0. 6y times -3 was -18y. And then this is dy dx, which was this. So I plugged in my dy dx. So here's this is what dy dx is equal to. And I plugged that in to dy dx. I still have square the bottom, and away we go. So then it's just a matter of simplifying. -18 times 3 is -54 times y. And that's still over 3y squared plus 2 over 3y squared plus 2. If you separate them out, this divided by this is the same as this times the reciprocal of that, right? So we wind up having 3 factors of 3y squared plus 2 to the third power. Yeah.
On the test, after you put dy over dx in, do you have to simplify it all the way like you did?
Yeah, so if you substitute dy dx in here, then, if we're looking here and you leave it at this where you've substituted dy dx in. So when I'm talking about you simplifying, if you leave it like that, I'm okay with that. I like to simplify it just because I always have this secret curiosity to see if things are going to separate or work out. So if I was working on something like this, these last two work out to be 12. If you're given a value to plug in, then you need to keep going. But rule of thumb, if you don't have a value that you're plugging in and you want to stop at something like this level, I'm okay with that. Is that okay? Say yes. Okay. All right, so next up is the review packet, and I don't want to spend too much time. You already had, so I posted the key. There was one mistake. Here I needed to make sure I did my 8 and my -8, but I didn't do my 2 and -2. So when we're talking about, I wanted to make sure you knew that I added that 2 and -2. Anything on the front give you drama that you want to talk about? All right. Let's talk about this page. Anything here give you drama that you want to talk about? Anything here give you drama? Go ahead.
Number 6.
Sure. So number 6 is the difference between differentiable and continuous is this. You can only differentiate a function if it's continuous. A continuous function means that I can trace it from start to stop without having to pick up my pencil. Every time I question my continuity, is it a hole, a jump, or an asymptote, a vertical asymptote? Not differentiable introduces this concept of a sharp cusp. And what's interesting is if you take your pencil, you could represent an infinite number of tangent lines that hit that only once because that sharp point makes it easy for you to do that. So if it's a sharp point, it's not differentiable. So if it's not differentiable where it's not continuous, but this only means that here's where I have a jump, or I could have made it a hole, but the not differentiable at -3 means I had a sharp point. Anything else for these, for the back of this page? So this is what we need to make sure you understand. Look how far we've come. It used to be that we had to do this to find the derivative, the instantaneous rate of change. Take the limit as the change between the x's approach 0. Okay, then we learned the power rule, and the power rule meant that I had to first multiply and then take the derivative. Then we learned the product rule, and the product rule meant that I had to do an awful lot of the first term times the derivative of the second term times the derivative of the first, and then the chain rule made that. So seeing where the chain rule evolved from, I think in this example is pretty cool. Because you should have gotten 8x minus 12 all 3 times. So whether you want to simplify and use the power rule, whether you want to use the product rule, or take advantage of this exponent and inside-outside function, I think it's pretty cool to see where that chain rule comes from. Next up, we have just some composite functions. There's no derivatives here, just, and then this table below is similar to the one we did for the warm-up. So hopefully you're feeling okay with that. These ones, did you get to the point where you had a favorite function? Where you're like, oh good, it's the f function, or oh, I like the sign. Because we gave you one trig, one exponent, one ln, and then you're plugging the different things in, looking at and finding your derivative each time.
Could you go before?
This one here? Okay, so when I go get my h function, that's 5 to the 3a, and my a is the cosine of x. So every time that I take the derivative of a base to an exponent, it's that same thing times the natural log of the base. Chain rule says now I have to talk about this. So when I take the derivative of 3 cosine x, I get 3 times the opposite of sine of x. Anything else? Go ahead.
So like let's say like with that same problem we have like 5 to the 3x instead of like trying to make this 5 to the 3x. Would we still use the chain rule for that?
So if you had h of x is equal to 5 to the 3x.
Yeah. Would that be the chain rule or just
Well, yeah, because you'd have to remember that 3, right? So your derivative would be, so the derivative of, and think of this as combined, would be 5 to the 3x times the natural log of the base. And then you have to take the derivative of what's inside. So that would be 3. So if I had a y there, it would be 3 dy dx. Okay? And then the back, the difference between implicit and explicit. And sometimes we can solve for y and find the derivative the old way, and that's fine. Sometimes we can't. So explicit is when there is that variable explicitly solved for. Implicit means the various variables are all mixed up inside. So when we solve these two ways, now what's frustrating about this is when you solve it explicitly, you get something that looks very different than when it's implicit. But if you want to test to see if you got it right, you can go ahead and see what you solved for y and stick what you solved for y in for y, and you can do that test. Here, y is equal to the natural log of 4 minus 2x. If I wanted to, I can stick that into there and see if I got the right answer. The whole idea of doing something implicitly is to have that y value for when somebody does give me an x and y. And that's kind of like what we're talking about down here with 13, 14, and 15. This is an explicit or an implicit equation. I've got the natural log of y and an x and everything, and then I've got that point. So I just dive right in and start taking the derivative. This is the product rule. Derivative first times the second plus the first times the derivative of the second. Don't forget your dy dx. So then I can go ahead and solve for dy dx. And as soon as I've done that, now I can plug in my x and my y. Like all that for -1. Are we good? All right. Pass your review packets, please, to one person. That one person, please take a journey to the inbox. You are, of course, allowed to keep your warm-ups out. No, I don't want to. You don't have to print it, just put it up here. And I'll just come look at it. It's like a little security mark. So go ahead and clear all this, sorry, I didn't mean to do this, so clear all the stuff off your desk, except for your warm-up, you're allowed to get that out. If you want to borrow a calculator, go get one. that stuff off your desk. Okay, make sure you got one now. It's like sticking together. I don't want you to think you have to do it twice. You're like, good God, no.